let's talk about how we deal with the properties. All right, so we're going to talk first about extensive properties and then intensive properties. And here we're talking about the usual ones, internal energy, enthalpy, and entropy for mixtures. And here we are focusing on the ideal gas mixtures. So if you want to find out the internal energy of our system in terms of kilojoule, you can do that in multiple ways. Either you could add up the internal energies of each of the components, right? So for example, if you have the internal energy of the component A as 1000 kilojoule, the internal energy of component B as 1800 kilojoule. Remember, note the unit here. It's not specific internal energy, but it's the internal energy as a whole, right? So if you want to find out the internal energy of the mixture, you just have to sum them up, right? So UM is simply equal to UA plus UB. So here it's going to come out to be 2800 kilojoule. This is one way of doing that. However, it's not very common to find the internal energy for a given component in the property tables. What we have in the property tables are specific internal energies, right? The small u's in terms of kilojoule per kilogram. So if you want to find out the small u's, well, it's pretty straightforward from here. We said big UM is equal to UA plus UB. And if you want to write this internal energy in terms of the specific quantities, you can write it as mass of that component times its specific internal energy, right? That is what UA is, plus same way mass of B times UB. So you can also write it as a summation of mass of that component times its specific internal energy. Okay, so this is when you want to get when you have the internal energy in terms of kilojoule per kilogram. If you have it in terms of kilojoule per kilomole, that is UI bar, then you just have to multiply it with the number of moles, right? Each of these ways are going to end up giving us the internal energy of a system at a given internal energy of a mixture at a given state. Okay, so we have the specific internal energy values given given for given in the property tables. So we can make use of, we're going to make use of this formulation very frequently, right? The mass of the component times its specific internal energy. Same way you can do it for other properties, enthalpy and entropy as well. So this is when you want to determine the extensive properties, right, which are in terms of kilojoule. But if you want to determine the intensive properties of a gas mixture, right, intensive meaning in terms of kilojoule per kilogram or kilojoule per kilomole, right? So here it's simply going to be the mass fraction for that component times its specific internal energy. All right. So again, if you're looking at a gas mixture, okay, so if you have a gas mixture of two gases A and B, the specific internal energy for gas A is 500 kilojoule per kilomole. For gas B, it's 600 kilojoule per kilomole. Then the internal energy, the specific internal energy for the mixture is not equal to UA plus UB, right? Because it does not make sense. These are specific values, right? If you want to take in the contribution of each, you got to understand how much is their mole fractions when you're dealing on a mole basis, or what are their mass fractions when you're dealing on a per mass basis. So the way to determine the mole fraction for the mixture the way to determine the mole fraction for the mixture would be to take in, using this formula right here, mole fraction of A times UA plus mole fraction of B times UB. Now, what is the mole fraction of A? Well, we can calculate it based on the number of moles given. So if I want to calculate the mole fraction of A, how much would it be here for this particular mixture? It would simply be number of moles of A divided by the total number of moles of A plus number of moles of B. So that's 2 divided by 2 plus 3, so that's 2 by 5, okay, 0.4. So the mole fraction for B would be 3 by 5 or 0.6. So when I plug them in here, 0.4 times UA is 500 plus 0.6 times UB with a 600, I'm gonna get something like 200 plus 360, so that's 560 kilojoule per kilomole. Okay, that's what we got here. So this is how you would want to this is how you would determine the specific internal energy for a mixture, right? So if you want to get the specific internal energy of a mixture in terms of kilojoule per kilogram, you have to make use of the mass fractions when you're dealing with kilojoule per kilogram, or mole fractions when you're dealing with kilojoule per kilomole. You could think of it as we are applying some sort of a weighting fraction to it, right? So where you're dealing with properties involving per unit mass, things per unit mass, they're going to involve mass fractions. Properties per unit mole, they're going to involve mole fractions. Any questions here in this slide or the previous one?
Clear, doctor.
All right. Okay, so then let's determine how can we get the properties for each individual component, right? Here we already had the value of u and ub given, but it's not something that's always given to us. We need to actually make use of property tables and determine. So the question is, what exactly do we need to determine that? Okay, so if you're dealing with properties such as specific internal energy, such as small u, or the specific enthalpy, small h, all we need to determine these values for a given component, the mixture component, is we just need their enthalpies, because remember we're dealing with ideal gas mixture. So all we need for this is the temperature, sorry, not the enthalpy. So if you want to find out the internal energy for the specific internal energy for some gas A, all you need is the temperature of the mixture. Okay, so enthalpy for gas A, you know the mixture temperature, you can go and get it from the property tables. But when we talk about the entropy, right, if you want to find out the entropy for gas A or gas B, well, you need mixture temperature for sure, but we also need the pressure. And here the pressure that we need is the partial pressure. It's not the mixture pressure. That's the key part here. What is the partial pressure? Well, for an ideal gas, the partial pressure is equal to the component pressure, and it's equal to the mole fraction times the mixture pressure. Okay, so we need this yi times pm quantity, which is the partial pressure of the individual component, and the mixture temperature to determine the entropy at a given state. Okay, here we are determining entropy of gas A or entropy of gas B, right? Entropy of, let's say, in general SI. That's all what we're trying to determine. And there's nothing new. We already know that if you want to get the internal energy or enthalpy, you just need the temperature. But if you want to find out the entropy, it depends on temperature and pressure. The only key part that I'm telling you here is it's not the mixture pressure, but this partial pressure that we need. Okay, so this point is pretty important, so I'm going to re-emphasize this a couple of times. So again, what I'm telling you is, if you want to find out the change in entropy for a given component, right? So we know from the formula for ideal gas, it's going to be S02 minus S01 minus RlN P2 by P1. But the pressures that we are dealing with here are the partial pressures, right? So these are Yi times Pm. Okay, so state 2 and state 1, that's why these are given different. The subscript 2 simply indicates the state that is occurring at, but the key part is it's for a component I. Okay, so the pressures in this formula are going to be the partial pressures. So you got to be careful when you use this formula for calculating it. This again applies for ideal gas mixtures only. Okay, so this cartoon is again telling you the same thing. It's not the mixture pressure, but the partial pressure. So now I have a quick summary slide to discuss all the different formulations that we have looked through till now. We started by talking about the mass fractions and mole fractions. Then we also came up with this definition for the molecular mass of the mixture in terms of mole fractions. There is one more definition though in terms of mass fractions, which you can refer to. But the key point is that the molar mass is simply equal to the mass of the substance divided by its number of moles, right? So if you want to find out, let's say, the number of moles, you can use this formula. If you want to find out the mass of the mixture, you can again use this formula. Okay. The idea is molar mass is always known from table A1. So either you know the mass, or you know the number of moles to find out the other. Now we also discussed that for entropy we need temperature and partial pressure, and these are the different formulations that you would need for determining these specific properties, right? In terms of per kilogram basis or per kilomole basis. All right. Any questions in what we have covered? If not, I will move forward and we'll start solving problems. All right. So let's go ahead and start solving the problem. But before there, I'll just mention again for the benefit of the students who joined a little bit later, who joined on time because we had the discussion slightly before. So about the quiz 4, you will have more clarity by 4 p.m. today. Okay. I may shift it to Monday or I may shift it to Tuesday. It depends on how we are going to arrange the extra classes if they are needed to complete the syllabus. Okay. I still don't know if
Doctor,
we need to do extra classes. Yes.
please try to postpone to Tuesday.
Yes. I would want to postpone it to Tuesday, but if we don't have any extra classes, then I may keep it on Monday. Yes, Tuesday is an option, but we don't have much time in the semester, so each day is important. But yes, I will consider your opinion, certainly.
We have test and quiz on Monday. It's better to make it on Tuesday.
Um, as I said, let me tell you by 4 p.m. You'll know for sure. All we are having is conceptual questions, okay? And apart from conceptual questions, you just have maybe one question where you need to make use of the chart,
Yeah, but
the chart for
it's
the enthalpy
difficult
distribution.
to take test and two quizzes in the same day.
I understand completely, and I would prefer to move it to Tuesday as well. But I would want to hear more about how the semester is going to go. Okay, so uh, yes, I will tell you at 4 p.m. Okay, and the situation where the quiz will move to Tuesday is when uh, you guys will be provided with some recorded lectures for the material that I will not be covering in the class, right? So I will be uploading some recorded lectures on YouTube. You'll have a pop quiz on this sometime on Saturday. I'll give you enough time. I mean, I'll give you maybe the entire afternoon for you to go through those. Like, you can go through the lectures anytime between today and Saturday, and then take the pop quiz on Saturday. Okay. So again, whether we're going to do this or not, you will know for sure at 4 p.m. today. Okay. So yes, I understand you guys are having other stuff also, but the next 2 weeks are going to be hectic. So you have to sort of you can't. I think it'll not be possible to have perfect preparation for everything. So yep, let's see what we can do. Now coming back, let's go and get done with this couple of problems that I want to solve for you today. So one problem that we're going to do is on closed system, which is this particular problem. The next one will be on an open system. So let's see what we have here. We have a gas mixture, right? It consists of 1 kilogram nitrogen, 1.5 helium. So this is a helium nitrogen mixture. And for information based on this information, we need to determine the composition in terms of mass fractions. All right. Then we also need to determine its composition in terms of mole fractions. And we need to calculate the amount of heat transfer in kilojoule that is needed to increase the temperature of this mixture from 22 to 67 degrees Celsius, right? We want to heat up this mixture, and we want to heat it up from 22 to 67 degrees Celsius while keeping the pressure constant. So it's basically a constant pressure heating process that we want to do. And we have seen this several times before. If you're having a closed system, and if you want to provide heat input into the system while keeping the pressure constant, well, what's going to happen is the temperature and the volume are going to increase, right? So from state 1 to state 2, the volume is going to increase, and basically for the volume to increase, you need to move the piston, so there's going to be some boundary work done. So this is the same case that we had when we were discussing the diesel engine as well, the constant pressure heat addition process. So this is something that always happens. Okay, now we also need to apart from determining the amount of heat transfer, we also need to determine we also need to calculate the change in entropy of the mixture for this constant pressure heating process. Again, this needs to be provided in terms of kilojoule per Kelvin. So looking for the big S, right? Not the small specific entropy. You're not looking for this. Looking for this big S, the change in the entropy itself. All right. So this is the problem that we have been given, and the first part A and part B are pretty straightforward. Okay, so we are going to do them the way we have discussed how to determine the mole fractions and mass fractions till now. Okay, so all right, so let's start with determining the mass fractions. So I need the mass fraction for nitrogen and I need the mass fraction for helium. So let's start with nitrogen. How do I determine the mass fraction for nitrogen? The only information given to me is the masses of the two components, nitrogen and helium.
What was the question, Doctor?
I want to calculate the mass fraction for nitrogen. How do I do it?
Is it 1 over 2.5?
Yes, excellent, Basam. That's all what we need, right? Mass fraction is simply the mass of nitrogen divided by the mass of the mixture. So this is nitrogen plus helium mixture. Okay, so mass of nitrogen is 1 plus 1.5, so 1 by 2.5, as Basam mentioned. So that's 0.4. Now mass for helium, either I could take it as 1 minus mass fraction of nitrogen because we just have two components, and we know that the sum of mass fractions for all components will be equal to 1. So if I do it, it comes out to be 0.6. If you want, you can also calculate mass fraction of helium as mass of helium by the mass of the mixture. So that's 2.5. So 1.5 by 2.5 will again give you the same number. That's as simple as determining the mass fractions. So that's for part A. Now for part B, we need to determine the mole fractions. Okay. How do we determine the mole fraction for nitrogen? We just need to determine one. We can find the rest, the other one from it. So let's focus on how do we determine the mole fraction for nitrogen.
Divide the weight in kilogram over the mole, number of moles.
But we don't have the number of moles. We are going in the right direction, but we don't have the number of moles now.
Mass.
Yes, we need to divide it by the molecular weight, and that's how we're going to get. So basically, first thing is to determine the number of moles, as Faisal mentioned. So we need to get the number of moles, and number of moles of nitrogen is simply the mass of nitrogen divided by its molar mass. Okay, the molar mass is given in table A1. So the mass of nitrogen is 1 kilogram, and the molecular mass is 28 kilogram per kilomole. Okay, so it's going to come out to be 0.035 kilomole. Now that's the number of moles. We also need to get the number of moles for helium, all right, to get the mole fraction. So that's mass of helium, which is 1.5, divided by the molar mass. The molar mass for helium is 4. So this again is something that you get from table A1. So the number of moles comes out to be 0.3747. Okay. So the mole fraction would simply be number of moles of nitrogen, which is 0.035 or 0.0357 to be more accurate, divided by 0.0357 plus 0.3747. So this value comes out to be 0.087. Okay, so that's the mole fraction for nitrogen. Once you have found that, you don't have to bother doing the same thing for helium. You could just write 1 minus 0.087 and get the mole fraction for helium comes out to be 0.913. Now, a very important point, I'm always here you're seeing that I'm just calculating the mole fraction for helium by taking it as 1 minus the mole fraction for nitrogen. Okay, this applies only if you're dealing with a two component mixture. If we had nitrogen, helium, and hydrogen in here, we cannot do this. You would actually need to calculate the mole fraction for helium, and then for the last one you could do this, right, where you subtract 1 minus the mole fractions of all other components. Okay, so yes, this is how we determine the mass fractions and the mole fractions. This part is simple and it's shown here. Okay, so part A and part B are done. We have determined the mass fractions. We have also determined the mole fractions. Now let's go ahead and deal with part C. Okay, we need to calculate the heat transfer that's needed to raise the temperature. Now here the system that we're dealing with is a closed system, right? And the energy balance equation for this closed steady state system can be written as energy in minus energy out is equal to the change in internal energy of the system, right? Because we don't have any change in potential or kinetic energies. Now, when we talk about a closed system, right, there are only two ways in which energy can get transferred. It can either get transferred as heat transfer or as work transfer. Okay. Now we don't have any heat going out of the system, and we don't have any work coming into the system. All right. All what we have is we have Qn. We are providing some heat to the system, as mentioned in the question, because we are heating up. We want to heat up the system, and we are doing some work, right? There's some boundary work being done. So minus work out. And this is equal to U2 minus U1, and this U is the total. This is not the specific internal energy, but the total internal energy, right? Or the internal energy in terms of kilojoule. Now, when we're looking at this equation right here, the boundary work that we need to calculate is for a constant pressure process, and we know that the boundary work for constant pressure process can be written as P delta V, right, or P times V2 minus V1. These V's are the volumes here. Okay, so I can write Qn as U2 minus U1 plus pressure times V2 minus V1. Okay, now P1 is equal to P2. So I could write this as P2, or I could write it as P1. Now I can combine this U2 plus P2 V2 and minus U1 plus P1 V1 and write it as change in the enthalpy. Okay, again, this is the capital H. This is enthalpy in terms of kilojoules. Now, the question is, how do I actually calculate this for this particular substance? Okay, how do we deal with this change in enthalpy? Or how do we take into account that we have two different substances, and the total enthalpy for the enthalpy in terms of kilojoule is not given for any of these substances, right? We have things given in terms of specific enthalpies. Okay, so the way to deal with it is the way we just explained when we were looking at dealing with mixtures. So the enthalpy can be written as mass times the specific enthalpy, right? So that's all it is. The big H is simply equal to mass times the specific enthalpy, and we have the specific enthalpy information given in the table. But here we also have been told that we need to make use of an ideal gas with constant specific heat, so we can sort of write the specific enthalpies as Cp delta T. Okay, so here we're looking at H2 minus H1, so we basically can break it down and look into the enthalpy change, the specific enthalpy change for nitrogen times mass of nitrogen, so delta H M nitrogen times delta H nitrogen plus mass of helium times delta H helium. How did we get this? Well, we had H2 minus H1. If you want to write H2, well, it's going to be mass of nitrogen times enthalpy of nitrogen plus mass of helium times enthalpy of helium. Okay, of course that's state 2. Minus the same thing, mass of nitrogen times enthalpy of nitrogen at state 1, and so on. Okay, so we just took this mass common and wrote the H enthalpy of nitrogen at state 2 minus enthalpy of nitrogen at state 1 as delta H. Okay, that's all what we have done here. All right, So coming back to this, we're going to treat it as ideal gas with constant specific heats. So we don't actually have to go and determine the delta H values. Okay, we can write it as Cp delta T. So it's going to be mass of nitrogen times Cp of nitrogen times delta T. Okay, plus mass of helium times Cp of helium times delta T. The delta T is same for both of them, right? That's the temperature of the mixture. Okay, but of course the CPs are going to be different. Now Cp for nitrogen needs to be evaluated, or Cp for any given gas needs to be evaluated at an average temperature. Okay, so if you look at the average temperature of 22 plus 67, 22 and 67, the average temperature would be 44.5 degrees Celsius. So we convert that into Kelvin because the temperature, because the specific heat values are given in terms of temperatures in Kelvin. So this comes out to be 317.5 Kelvin. Okay, and from table 820, the value for Cp of nitrogen is can be taken as 1.039. Okay, so this value is given in table 820 at this temperature. It's going to be a function of temperature. You change the temperature, things are going to be different. Now for helium or for any other noble gas such as argon or neon, right? The specific heat is not a function of temperature. It's a constant. So it's a constant which is 5.2 times R, where R is the gas constant that you're dealing with. So the R value is going to be different for different gases for sure, right? So Cp of argon is going to be different from Cp of helium, but the formula is going to be remaining the same. It will be 5.2 times R, and you already calculated the Cp of argon when you were solving the homework. So R would be simply the universal gas constant 8.314 divided by the molar mass. The molar mass for helium is 4, so this comes out to be 5.192. Okay, we have the CPs now. So here we can go back and write Qn is mass of nitrogen, which is 1 kilogram, Cp of nitrogen 1.039 times delta T. Now delta T here for 67 minus 22, that's 45. Okay, plus mass of helium 1.5, Cp of helium 5.192 times delta T, again 45. So Qn comes out to be 397.2 kilojoule. Okay, so as you can see, we started off with the things that were known to us. We started off with a general energy balance. We came up with this formulation in terms of S2 minus H1, right? Enthalpy changes, and we just broke down the enthalpy changes, right? The total enthalpy change of the mixture is equal to the enthalpy change of each component within the mixture. And to find out the enthalpy change of each component, well, we simply made use of we multiplied the mass of that component with its change in specific enthalpy. Okay, the reason we multiplied with the mass is because this is specific enthalpy, not the total enthalpy. Same way we did it for helium, and this is what we got.